In this video, we're going to be looking at a paper called Adaptively Accelerating MapReduce and Spark with GPUs, a case study. This paper essentially takes a computer which only has CPUs and a computer which has CPUs and GPUs, and then it runs machine learning algorithms on both of them and compares them. And it finds that running the algorithms on a GPU and making use of the GPU has a much shorter runtime than just the CPU. So we want to show that machine learning frameworks and algorithms can be can be sped up by running them on GPUs. What sets the paper aside from other papers in this area is that other papers haven't considered the full end-to-end runtime of the frameworks, while this paper does. So this paper will look at taking the memory from the CPU and downloading onto the GPUs, and the time that takes and what kind of impact that also has on the algorithm, which other papers haven't really looked at. This also comes with some challenges which other papers haven't looked at, which will be discussed later on. So the frameworks that we're going to be using in this paper are the default implementations of Hadoop MapReduce, M3R, and Apache Spark. Now these papers are all industry level, these frameworks are all industry level frameworks and are very common, which is why they've used them. They're very popular, very common, and so they're good starting points to test these algorithms on. Now we want to test four main machine learning areas. We want to test clustering, classification, linear regression, and dimension reduction. And we'll be looking at different algorithms for each of these areas. So all algorithms are written in Java, and they use the default implementations from the APIs, from the frameworks. So there's no custom APIs used to do these. So for clustering, we're going to be using K-means++, which essentially takes the squared area between centroids and instances, and then uses that to try and cluster nodes together, instances together. Classification takes, we're going to be using multinomial logistic regression, and with our regression we're going to be using multiple linear regression. For our dimensionality reduction, we're going to be using principal components analysis through singular value decomposition. PCA is a very common algorithm, at least at the time of this paper, and is a good choice for this area. So some of the challenges that this paper came up against was running the main algorithm on the CPU and then scheduling tasks to the GPU or the CPU based on which one was more efficient. So some tasks were better run on the GPU and some were better run on the CPU, and then scheduling these and running them in parallel was one of the main challenges. They ended up coming up with a simple and efficient solution of using atomic counters. I haven't gone in depth in this video on that, but it's a good finding within the paper. Another problem they had was warping, which is where groups of cores diverge from the main execution thread due to conditionals within the code. For example, an if-else statement. This is because with the NVIDIA GPUs, they have sets of cores, and when a main execution thread is run, when you meet a conditional, it'll split off and use different cores for each path, and then once the conditional is finished running, they'll choose a path to continue downwards. This allows them to run the code much faster, but it does mean that sometimes you're not using your cores to the full efficiency that you could be. To get around this problem, they minimized the use of conditionals, or if they couldn't avoid that, they would just not run those conditionals on this GPU and purely run them on the CPUs, where they didn't have that warping problem. They found that utilizing the GPU memory effectively was quite difficult. The frameworks themselves couldn't run it properly, and so they would have to manually allocate GPU memory and so on by storing the data appropriately and doing it by hand. So what are some of the results that they found? Well, they found that running the algorithms on a CPU and GPU computer was a lot faster than just the CPU. So they greatly decreased the processing time required for these algorithms. Here we have a few graphs taken from the paper. The first column, the leftmost column, is the MapReduce framework. The middle one is the main memory MapReduce, or the M3R. And finally we have the accelerating Spark framework. Each row is a different machine learning algorithm. And there's a lot more. There's a few other tables with different variations of each of the algorithms. But I just simplified it down to one page so we can more easily see what's going on. So we can see that each graph has about 6 pairs of bars, and each pair has a left bar and a right bar, and the left bar in almost every case is larger than the right bar. So the left bar is the amount of time it took to run the algorithm purely on a CPU computer, while the right bar was with a GPU as well. So we can see that the time taken is considerably slower, especially with the k-means algorithm. Running with multiple nodes just incredibly drops the amount of time it takes to run these algorithms. So what are some of the conclusions we found? Well, the paper provided some app solutions to the challenges that we found. We can see that we had the scheduling and parallelizing challenge, warping, and then utilizing the GPU. These are problems that other researchers will find come up against and other people in the industry, and so having good solutions to these is a good finding. They also found the main point of the paper was to find how much faster it took for a CPU and GPU to run than just purely a CPU. And they found that it took a lot faster. I have 10 times here, but some of these from this graph was 21 or 25 times faster, which is very considerably faster, and it's definitely worth implementing for really large algorithms and large data sets.